Hello, my name is Howlana Matamanisha from Group for Computer Graphics, and our project is a multi-agent video storyboarding for accelerated refugee education for the competence-based content authoring. So our project it usually focuses on how multimodal AI, this is AI combining text, images, and audio, can help improve learning for the refugees in Uganda under the Uganda's competence-based curriculum. And the keywords of our project the keywords, we have computer graphics, which is a field for creating and manipulating and also displaying images and other visual content using computers. Visual programming, which is programming by assembling graphical blocks or visual components instead of writing text-based code. And then a competence-based curriculum. This is an education approach that focuses on the learners demonstrating specific skills, abilities, and real-world competences rather than just memorizing content as delivered by teachers. Then generative learning technology, which stands for this is AI tools that create new content such as images, audio, videos to support learning and teaching. Then also interactive storytelling, which involves a digital narrative where the user actively influences the stories through choices, actions, and other interactions. Multimodal AI, this focuses on artificial intelligence systems that understand and generate multiple types of data such as text, images, audio, and videos together at once. Vision language models, these are AI models that jointly understand images and text, enabling tasks like image captioning, visual question answering, and scene interpretation. So briefly, that is what our work stands for. So Uganda is currently a home to over 1.74 million refugees, and of these we have about 890,000 learners who are enrolled in schools through the accelerated education programs. But these accelerated education programs face challenges like limited resources, language barrier, and trauma-related learning gaps. So our project introduces an AI multimodal content authoring systems that replaces the manual 3D designs with multimodal AI such as 53.5, which handles scripting, and the Omni LM that ensures semantic matching, the good taste that uses local voiceovers to create interactive story-based lessons so that we can help the learners catch up. Many times the learners come from different backgrounds. Others come from Arabic-speaking nations, others French, others English, and then they all have to be put into the same school, and they have to learn at once. And many of the content they use is linguistically mismatched. It is outdated, and most of it is text-based. So, and also like you coming from a different background and you come into a system where also the teacher is using an accent you can't easily follow. So all that informed the decision of creating our tool that uses the competence-based curriculum input. Then we have the AI processing. Then from the AI processing, we have an animated story, which is then delivered to the learner to learn. Yeah, so it involves visual programming, multimodal AI, and an offline fast output for the videos since they are to be delivered in a resource-constrained environment on low-end tablets. Previous research has explored AI in education, especially for adaptive learning and language support, but most of these systems were built for the Western education systems, and they require stable internet and powerful devices. For example, the Mini-GPT-4 in 2023, which proposed an approach that replicated the GPT-4's vision language capabilities with compact architecture to support image captioning, dialogue, and visual question and answering. But this requires a very stable internet, and there's no offline usage, which is non-suitable for the resource-constrained environment we are developing for. Then Aqua 2.5, which proposed a scalable multimodal reasoning for documents, images, and videos, but then it requires large computational infrastructure, still non-suitable for what we are developing for. The Video Llama, which proposes aligned audio and visual features for instruction-tuned video comprehension, but then it also has a heavy computational load, and it is also impractical for the Ugandan refugee schools, and it lacks localized content generation. And then the 5.5, which proposes a high multimodal efficiency with over 4.2 billion parameters, but then it's still heavily dependent on GPUs and requires reliable internet and lacks culture and CBC contextualization. Then we moved on to the Stable AI Fusion, which proposed an architecture and training improvements that yield higher image fidelity and better compositionality, but then it also requires a higher compute memory and needs earlier SD versions, which is also not suitable for the kind of environment we are developing for. And then the Google text-to-speech, which presents methods for zero-shot multi-speaker, text-to-speech, and voice conversation over the speaker, but then the quality drops on very noisy or extremely short inference samples. So moving on to the problem statement, there are two core problems we are trying to address. First, the domain-specific problem where the refugee learners lack access to high-quality, localized, and up-to-date learning materials. So most of the AEP and CBC resources are linguistically misaligned, and they're also linguistically misaligned and majorly text-based, and we do not have internet connectivity for the online resources. And then the computational problem, where the challenge lies in how can we produce pedagogically aligned, multilingual, culturally relevant, offline-ready, interactive, story-based lessons from the directly existing CBC content to give to the learners to help them learn faster and catch up. And so our research was basically guided by 4 questions and objectives. So we asked ourselves, how can we develop an offline fast authoring pipeline for education content creation? And then how can we generate animated multilingual CBC modules tailored for the refugee children and environment? And then how can we evaluate the learner outcomes in diverse refugee settings to measure impacts to see are the learners really learning? And then how can we evaluate the learner outcomes? How can we release an open access template and tools for broader MDO adoption? And those are research objectives. And then for the research questions, what framework can effectively support CBC aligned visual stories? What models are optimal for generating offline multilingual content? And what impact does this approach have on engagement and retention? And then how can we scale these open access visual templates for wider use? And from what we've done so far, we've been able to develop robust structured lesson scripts. We've developed a system to generate structured lesson scripts perfectly aligned with the CBC topics. And then from the teacher's input or prompt, we are able to generate a script from the CBC topics that captures everything. And then from the script, we have an evaluation framework that where we implemented a comprehensive way to assess the script quality, the topic alignment, the research relevance using semantic similarity and readability metrics. So after your prompt and after your prompt, we have after the test prompt, we have a generated script, and from this we can evaluate your script before you move on to the scenes and the visual story, the video later. So we first assess and to see is the script quality does it have very good quality? Is the topics aligned? The resource the topics aligned and using semantic quality and readability metrics, and then future datasets are here we prepared and structured CBC aligned topic datasets, which are essential for automated content generation and effective lesson planning. And then data-driven insights, where we provided critical insights into the script coherence, topic coverage, and engagement potential, thereby guiding future multimedia lesson development. So moving on to the methodology and system architecture. So our architecture represents an end-to-end AI system that converts the curriculum-aligned prompt from the teacher's prompts to integrate natural language processing, generative storytelling, and multimodal synthesis, and including the storyboard generation, and then to the video, to the audio generation. Then after the video, combine all this together to have an informative video. So our architecture comprises of 6 interoperable modules. One, which is the authoring interface, which is a web-based portal for educators to input and edit the CBC aligned lesson manifest. Then the retrieval augmented generator, graph retrieval augmented generator, which is the second layer, which retrieves and injects culture relevant knowledge into the generation prompt. Then the storyboard generator, which this is where we generate the storyboards based on the generated scripts, and the multimodal synthesizer integrating the diffusion-based image generation, and the multilingual text to speech with lip syncing, and then the video composer, which assembles all the assets into a deployable video format using the CPU efficient metadata, and then we generate a video. So these are the different modules of the architecture. So so taking you through from the text input, following the position of my cursor, from the text input, the process begins with the curriculum mapper, which ensures that all generated content aligns with the intended lesson outcomes. So here we use the transformer encoder to interpret the text input, and then the similarity layer. Then the similarity layer that compares the input text with the predefined curriculum standards. And then here the output from the curriculum mapper is a redefined version of the user's input that serves as a foundation for the story generation. And then we move on to the story and the script generator. So in the story and the script generator, here we create a narrative flow and instructional script. So in here, we have a token embedding and positional encodings to understand the linguistic content. And here we use a multi-head self-attention mechanism to capture the relationship between the words and the phrases. And then from here, we produce a script draft which is a coherent educational story outline. And then remember, as I said earlier, we can assess the quality of the script to see if this is because the quality of the script informs the scenes we are going to have, and from the scenes, the storyboards, and then also the video. So here you can see from the script quality, you can see this really what I intend to do, because it is a very informative script, as I'll share later in the demonstration. And then from there, you can choose if you are to continue or you need to redefine the prompt for a better script. And then from after the script generation, the script then passes through the graph retrieval augmented generation, which enriches the script with culture and contextual relevance. Then after here we have a culturally augmented script, and then from here we move into the text encoder. Here the script is converted into latent representation of the image and the video generation. The text encoder embeds the script into a format which is understandable by the visual generation modules, and then also we have the ENS denoisers, which uses the cross attention mechanisms to align the texture meaning with the visual features. And then the output is a latent visual concept that guides the storyboard generation. So then I move on to the other module, which is the storyboard generator. So this component visualizes the script into storyboard frames, which are a sequence of images showing how the lesson will unfold visually. So here we use the attention decoder to interpret the encoded text into the visual scenes, and then a vocoder that converts the narration text into a narration audio file. And then we have the VAE decoder, and which generates diverse, detailed storyboard frames. And so the result from the output here is a narrated storyboard skeleton of the instructional video. And then we move to the lip sync encoder and generator. So at this stage, we have to synchronize the facial movements the generated visuals with the narration audio. So we process the visual characters at the first, and the audio encoder extracts features from the narration audio, and then after the lip sync, the syncness discriminator ensures that the lip movements and the audio are perfectly aligned. Excuse me. And then after we produce a synced video clip. And then from here we move on to the video composer, which is the final component. And here all components and all assets come together into the video composer. So we arrange here in the video composer, we arrange the different storyboard scenes, and we arrange the video storyboard scenes in order, and then we add smooth transitions and visual effects, and then we provide a final video which is fully synced, culture relevant, and curriculum aligned to the learning asset. And so in summary, this architecture combines NLP, natural language processing, audio synthesis to automate educational video production. And so moving on to the different modules that we employ in our pipeline, starting off with the TTS. So the teacher patch reads the letters and turns them into a song map. For instance, if you type like a sentence like time, so the teacher patch reads the letters and turns them into a song map, which is also known as the mouse spectrogram, and then it chooses attention to match its sound to the right words without skipping. And then the singer part, which is the WebNet, turns the song map into a real voice with pauses, tone, and emotion. And then from here, it sounds like a real person is reading aloud in many languages. And then moving on to the Stable Diffusion XL. So so this is more like a dream painter. So if you say, for instance, if you say draw a line wearing a crown in a village, so then the computer starts with a pure noise like to this no. It asks your word for help using two smart word checkers, which is the clip. And then after there's a step-by-step iteration for over 50 times, and then it cleans this noise. And then from here we shall have the the image appearing of a lion which wears the crown. And then the second part, which is the artist, it is the refiner, it adds sharp details to the image. And then at the end of it all, we shall have a beautiful image which is which is over 1024 times 1024 pixels picture on a normal laptop. And then from here we move on to the Web2 lip sync. So this is more like a mouse magician. So if you have a video of someone talking, but then you want them to say new words, and so if you have a video of someone talking, then you want them to like actually pronounce the words. So it listens to the audio and then finds the lip shapes needed. It watches the face and remembers who they are, and then it paints new mouth movements. So it paints new mouth movements frame by frame, and only the lips move. The rest stays the same. So then a judge, which is a sync net, checks the lips and the lips match the sound. So if yes, then you can then if the lips match the sound, then the generated video appears to be talking. And then moving on to the Omni L6 V2. So this it is like a sentence fingerprint maker. It uses so you give it two sentences. It shoots both with a tiny brain, which has about 6 layers and very fast. Then after it turns each sentence into a fingerprint, which is a list of about 384 numbers. If the two fingerprints are almost the same, if the two fingerprints are almost the same, that means one thing. This is perfect for searching stories in different languages in English, Uganda, and even applied for offline usage. And then from this, we move on to the dataset description. So we use a high quality dataset, which was high quality dataset, which was prepared and it underpins the alignment culture. It underpins the alignment, cultural relevance, and the linguistic fidelity of all generated components. So it was all data was meticulously extracted from the Uganda's competence-based curriculum and the accelerated education programs. So it has 26 topic level requests specifically for the accelerated education program level 1, term 1, ensuring that it was focused and it was a manageable scope. And the primary variable for our dataset was competency, defining the skills or abilities that the learners are expected to acquire. So so this is our deployed model. This is our deployed tool. So when you come here, you enter as a teacher, you just enter a simple text prompt. For example, teach students, teach division, and then you submit. But the video generation takes really long. It takes a lot of time. As you can see here, it takes quite some time to generate the video here. So I'm just going to take you straight to the generated video. But before I take you straight to the generated video, I wanted to share like what happens in the background as this is running, like what is happening. So in the background, when the model is running, as when you enter a prompt, we first generate a fully detailed script that is explaining everything as it is going to happen. So when you as a teacher, you simply just enter your prompt, and then we first generate a script. Because the quality of the script determines the quality of the scenes, the quality of the audio, and it determines everything. So that's our script. This is a sample script of what is generated from a prompt. So we limited it to 3 scenes because of time. Because when there are so many scenes, the model takes a lot of time. The pipeline takes a lot of time to generate this. So we needed to have a demo video, so we limited it to 3 scenes. And here you can see it's how it breaks down the scene from the introduction, then it gives a visual description of what the scene will be like, and also provides a narration. The visual description is used to inform the kind of image that will be generated, and then the narration is also used to inform the audio that follows that image. And then we go to scene 2, which is an example, same the visual description and the narration. Then from there we move to the video, the generated video, which I'm going to be showing you later. Videos from our pipeline, we have this. So this was a video demo demonstrating how our developed product works. And then so it goes on and on. We had quite many, but for the presentation I decided to choose this. And so continuing. So for the meta selection and deployment, as I had said earlier, our pipeline is a multi-agent system. So we have the 5.3 mini. This is what does the text understanding. This is for generating the script. It's important, and the Omni L6 V2. This is to ensure that the script is aligned to the curriculum and the stable diffusion. This also to generate the images, and the GTS for the speech synthesis is the one that provides the audio generation. And then the Web2 is supposed to use it for lip syncing when we reach that point of generating fully animated scenes, because now our scenes are all static and we just combine them. And then the MoviePy is used to assemble all the generated assets, and then we create a video. And then for our IP assets for the default products that we have, our data was created by us, it's custom. Then we have a robust script generator and the video assembly workflow and multi-agent system with all that is unique and it should be patented. And then there is interaction design. And then for the limitations of our proposed solution, we have the generated images. You don't fully capture the exact meaning or instructional intent of the script. So our images are lacking. And then the audio is for a white man, and we want to clone our own audio so that the generated audios are related to, you don't hear white man speaking. And then the generated images lack motion. We want to fully animate our scenes, and we were very limited by the complete resources, and it was quite a hassle here. And then so our pipeline fully demonstrated how a multi-agent system can be used to combine text, image, audio, and video generation. That system can be used to create educational storytelling videos aligned with the Uganda's competence-based curriculum. So, and while maintaining that, while keeping in touch that the generated videos are culturally relevant, and the imagery and also the audio is fully with generated audio. Though our images are not fully animated, but we demonstrated that we can use the pipeline to create our images. So that is in the talks. And then so the future works want to transform these images to be fully animated with a lip sync while also maintaining the background of the image, so that as someone like the background of the image is maintained, then we want to conduct pilot studies with the children learners and see how our tool helps. Then we want to apply automatization for the low resource settings, such our models are not like very resource hungry and they can be deployed on low resource devices. And then we want to also adapt our tool for a multilingual context, so that we do not only support one language, but then we support multiple languages.